Hello. Okay, thank you. So welcome to this section. And I am very proud to introduce this section 8. This section is about machine learning and models. Of course, as you might know, this section is mainly devoted to the development of statistical models and machine learning and statistics. So we start on time. Then I am happy also to introduce our speaker here. And mainly here we have 4 speakers. First of all, I introduce very briefly myself. I am Fulvia Pennoni. I'm working at University of Milano Bicocca, and I am part of the program committee. So I also take the chance to mainly thank all the other colleagues who contributed with me to these events. So thank you to all. And mainly I would like to first very briefly speak about our speakers. They are on this list. So we have Luís Silva. He is a data scientist at the Food and Agriculture Organization. Then the next speaker will be Andrea Sottosanti, who is a postdoctoral researcher at the University of Padova. And then there will be Apostolos Chalkis, PhD student in computer science from University of Athens. And then will be Riccardo Corradin at the end, who is a postdoctoral researcher at University of Milano Bicocca. So I will leave the speech to the first speaker, and please I remember you that we have to be on time. So when the ring start to bell ringing, when the bell is start to ringing, so please stop the talk, and then we can continue after all the presentation to speak about the topics. So thanks a lot. I ask to Luís Silva to come on stage, please, and to introduce his work as well as the co-authors of the work. Please, Luís, if you can see me.
Yeah,
good morning, Luís.
Good morning.
Nice to see you today.
Nice to see.
Share with us your knowledge. So thanks a lot for your presentation. I leave you the stage. I close the camera, and you will sing the ring when you have to.
Okay, thank you very much, Fulvia. So first of all, I would like to say thank you and congratulations to the organization to be committed to make this event real. So even in this bad situation in all the world, not only Italy. So thank you and congratulations. Let me share my screen. Here, 1 second. Can you see my screen? No. Okay, maybe now you can see. Right? Okay. Okay, thank you very much. So I will talk about this work. It's a joint work with some couple of friends from Brazil. I'm Brazilian. I have a background in statistics. I have a PhD in statistics and master, and my bachelor is also in statistics. And this work was developed by a group of friends that used to work on some lab in the Federal University of the Minas Gerais. That is one of the main universities in Brazil. So the title of our presentation is Voronoi, Linkage for Spatially Misaligned Data. It's a long title, but in the end, what we want to solve is the question, the subtitle, how to transfer knowledge from areas to points. So if you have one variable that you measure at the area level, and then you would like to join the area and points. So you can find me in all the social.
Sorry, Luís, I just interrupt you for a while. Someone is asking me if you can close your camera in order to see better the slides. Thank you.
Okay, thank you. Okay. Now it's okay. So you can find me in any social network by just type LG Silva, Twitter, GitHub, LinkedIn, and there's my personal website where you can find my CV and some project that I have worked some years ago. Of course, feel free to text me through email, so feel free. First of all, I have to introduce you in the Brazilian electoral system, just to understand our motivation. So in Brazil, we have the three main political levels: federal, state, and municipality. In these three levels, you have to elect one candidate. You have to vote, and each candidate can be elected if they receive the measured vote of all the voters. So in some case, for example, in the state and the federal level, you need the second round. So it depends on the population and also the difference between the two most voted candidates. So it depends. In Brazil, the voting is mandatory. So all people from 18 until 65 years old have to vote. It's you must vote. So to vote in Brazil, you have to go to the electoral section, which usually is a school or a community center. I just show in the left side one map. This map is the Belo Horizonte seat. It's the capital of the Minas Gerais state, and each point represents the one electoral section. So it's the one image, one example of the electoral. So here the voters have to go there and select your candidate, and then it's done. But each people can go there only if this electoral section is assigned for her. Otherwise, you cannot go to any electoral section. So it depends on your home address. So you can find, for example, for one point here, the people around this point goes there to vote. So it's a more especially distributed. So our idea is, if you have at this point that you have the percentage of the votes and some variables related to the people that go there to vote, and also you have the tract census, that is the area. If you see, I'm not sure if you can visualize well the polygons behind of the points, but each polygon, each area, small area, is a tract census in Brazil. So in this level, we have, for example, variables like income, the number of the white people, the number of black people, the literacy of the people in that area, and we have some another information like density, and we have a lot of information in this level at the area level. And you'd like to join the point and the information that you have in that area, because you can try to understand better how the people are voting in each area of the one seat. Usually in Brazil, all the election analysis is only at the seat level. So, but if you see, you have you can have a more detailed information if you could join the two source of the data. So you'd like to extract data and information from areas to points. So the first approach is the called by naive approach, that you can just, if one point touch in the specific polygon, specific area, so you just transfer all that information to the point. So if one electron section belongs to the one specific area, so all variables associated to that area will come to the point. The main issue in this case, you lost a lot of information because you don't have one point, one electoral section in each polygon. So you lost almost 90% of the data. So it's not a good approach. We propose this Voronoi tessellation. That it's Voronoi. I don't want to spend a lot of time to explain what is the tessellation here. But suppose that you have a set of points, and then you'd like to create a cells that involved each point. The cells, it's the maximum cells the maximum area for each point, and when you select any point inside of this each cell here, it will be closer than the center, than another cell. So that is the small example. Our approach, instead of using only the that areas, we created the cells around each electoral section, and then we transfer the data, the information proportionally the intersection. So if you see in this slide here, we have one point, red point here, that is the electoral section, and the blue area is the Voronoi cell, and behind of the Voronoi cell we have the tracked census. And when you intersect the tracked sensor, you just transfer. For example, if you have the variable income, and the intersection is around 20%. So 20% of this information goes to the cell, the Voronoi cell. So here it's like the weight average for the specific electoral section. And the idea, once you have this, once you can transfer this knowledge, this information, of course, all the information has to be a numeric information. It's not possible to transfer nominal information because you need to apply this proportional in each variable to transfer to the electoral section. So in the end, what you can have at the end of the product, it's how are your neighborhoods are voting, because here we can go directly to the inside of the seat in the most detailed information, and you can see here one of the example. After apply our methodology, you have in the left side the census tracts here, and the right side you have the polygons for each electoral section. You can see that you can keep the spatial correlation here, where it's high. Here it's high in left, it's high in the right side, and when the value is low, it's the same happen. So you can keep the correlation. So you can use the statistical model to verify the spatial correlation. For example, you don't lose this structure, and if you look to the naive approach, it's not possible because it's not continuous. You lost the neighbors between the cells. So the second example, you can match the votes that you find in the electoral section and the income that comes from the census. So you can see again, you can correlate these and run regression models and the spatial models to identify any correlation in this level. We have one Shine app to explore our results, and of course the methodology it's explained in detail each step. I don't want to. I just would like to show and motivate you to read our methodology and visit our Shine app. There, I'm not sure if I can go to another tab because I shared only one tab here. But if you go in our Shine app and click on the tab candidate, you can see the same map. Here it's the votes that the candidate has received, and the left side you see the income. So for this candidate, you can see that the people that has the high income doesn't vote in these candidates, because here it's concentrated the people with has more money, let's say this, and for light red, it's people that doesn't have too much money. So you can see that it's like a mirror, inverse mirror in this two map. The concentrate of the people that have money here and that doesn't vote in this candidate. So if you change, of course, this parent here and select, you can visualize better, and of course the variable that you want to see as well. So our conclusion here, our approach seems to be efficient to aggregate information from areas to points. Another good improvement that you can visualize and in high level of detail. I think it's the most important. You can see these at the neighborhood level, and you can learn how the people are voting in our community. And of course, it improves the interpretation of the statistical for people that doesn't have a good background and in statistics. So it is the brief conclusion, and feel free to read and contact me for any time to explain, and of course to share knowledge and maybe contribute in our work. So thank you very much. Again, it's my contact, so can feel free to contact me anytime. And thank you the organization, thank you Fulvia. It's done.
Okay, thank you very much also to you to be on time, and please stay with us for the question later. So I ask to be on stage now to Andrea Sottosanti. So please, Andrea, join us on the floor. Still, we cannot see you, but we are waiting for your presentation. Thanks a lot to Luís in the meantime. Okay, hi Andrea. Good morning. Nice to see you, and I leave the stage for you, so please be on time as well. And I close the camera and share your slides, and close your camera, please.
Okay. Wait.
No problem. Take your time.
So can you see my slides now?
Just a while, I cannot see them.
Maybe I should stop my camera.
Yes.
You see the slides now? Fulvia, can you say yes or no, please?
Right now, I cannot see the slides, so.
Okay, maybe we can. Okay, can you see them now?
Let me check. Really not yet. So please, if someone from the administrative staff can help.
Wait. Okay, now you should see.
Okay, perfect.
Okay,
Go on.
sorry for the technical problem. Good morning, everyone, and thank you to be here. So thank you to be here at my talk. And today I want to basically talk you about astronomical source detection and background separation. So maybe with these words, someone of you has in mind something like this. This one is a fresco of Galileo showing to the Doge of Venice how to use the telescope. And in general, in fact, the astronomical source detection is that part of the astronomy which wants to detect and study new celestial objects in the sky. But nowadays, things are quite different because of now we have available images like this one. So huge collections of data which are able to describe very well the sky in all the possible directions. You can see here many spots corresponding to the signal of maybe high energy astronomical sources, but there is also a lot of background contamination which extends all over around this kind of maps. And at the base of this map, we have photons. So we have infinitely small particles for which we know the longitude and the latitude, so the bivariate coordinate in the space, and the energy as well. So three variables, a very easy setup. The goal of this analysis is to locate and quantify the signals of astronomical sources. So basically the question is, where are the astronomical sources? And let us quantify their intensities. In order to do that, we want to separate the background contamination which extends all over around this kind of map and is particularly common in astronomy and physical science. And so in literature there are a lot of attempts in order to provide methods to do source extraction, signal source extraction, and most of them are in the class of single source model where they concentrate just on a single part of the map, a very small region, in order to extract a source at a time. But what we want to do is to go further in the class of multiple source model where you take a larger map, a larger area on the map, and you want to detect simultaneously multiple sources. But the problem is that these kinds of methods usually require a previous knowledge of the background contamination. We want to go further on this step. So our proposal starts from a very simple setup. We just take a collection of photons for which we know the longitude and the latitude, as I said before. And the density function of this bivariate variable can be written as a mixture of two elements. The first one is a source model, S, which basically describes how photons from the sources spread in the space. And at the same time, B describes how photons from the background spreads all over around the map. And as I told you, I have a single photon, but I don't know whether it comes from the sources or from the background. And for this reason, I have a mixture model, and delta is the proportion of photon emitted by the sources. So let's now characterize these two elements, S and B. Regarding the sources from a physical point of view, there is no reason why a source should be spread. The signal of a source should be spread. Basically, it's a Dirac distribution in the space. Okay, but because of the telescope, the signal is spread around the location of the source, and the way how it's spread is a well-known function, which is the point spread function. And the variability of this function, as you can see here, the representation, the variability of the function depends from the energy of the photon. So larger is the energy and preciser is the detection of the photon. The only unknown parameter is the location of the source, which is the center of this distribution. But as I told you before, we don't have any a priori information on the number of sources and their location in the space. So we pull all this information together and we propose a model of this type. So this one is an infinite mixture where the kernel is given by this point spread function, which is this bivariate density function, and F is a mixing measure which is sampled from a Dirichlet process prior. So basically, we are inducing a possible infinite number of sources in the map. And with this prior assumption, this prior distribution, we are assuming that they can be anywhere in the analyzed map. So this one is for the source model. But let's now pass to the background, which is usually background is something which is unpredictable, but we know that it tends to be smoother than the signal of the sources. So we recall a very well-known function, which is the normalized B-spline function of order k, so with a vector tau of k plus 1 nodes. And this function is very nice because of it's always positive or at least null, and it's unimodal. And it's very easy to be normalized. So we can use that as a density function, and we define this bivariate kernel for the longitude and for the latitude. You can see that it's unimodal and takes many possible shapes. Our idea is to mix it infinitely again, proposing a second Dirichlet process mixture where now the kernel is taken as this bivariate B-spline kernel function. Okay, and the prior distribution on the nodes is set in such a way that you can preserve the order of the nodes. So the nodes of the spline are the unknown parameters. Okay, and so we have a mixture of Dirichlet process mixtures, one for the sources and one for the background. So it might happen that because of our model is quite flexible, you can occur in some misclassifications problems. For example, it might happen that the model of the sources captures part of the background and vice versa. So in the first case, we cannot really prevent false positives because of it is just due to the structure of the data. But we can work on false negatives because we can avoid the background model to capture the signal of the sources by forcing the B-splines used in the Dirichlet process mixture of the background to be larger than the function, the point spread function used to detect the sources. And we can work on the variability, the variance of the B-splines used in the background Dirichlet process mixture, using the formula provided by Carlson in 1991 and forcing them to be larger than a certain constant, which is C, which is a kind of smoothing parameter, actually. And from some simulation experiments, we showed that C equal to 1 is enough to guarantee a good separation of the sources, the signal of the sources and the background, and prevents the type 2 misclassification problem. So this is very good. So this is just to summarize the structure of our model. So we have the mixture, the mixture at the top, which splits into sources and background. Then this one on the right is the background mixture model, and the one on the left is the source mixture model. So now let's pass to an illustrative example. We have here the signal of 9 sources simulated using the Fermi-Lat point spread function. So we are using a kind of real setup, and we simulated also a moderate background using another tool from the Fermi team. The Fermi is a telescope from the NASA. We give a kind of a priori specification of the parameters in order to have a larger number of expected sources than the number of background components. We run multiple times the chain in parallel, and then we merge the results in order to obtain a unique final chain. And these one are the results regarding the number of sources detected. You can see here that the true value is 9, but actually the distribution gives a large probability to larger values like 12, 13, and 14, and so on. So what's going on here? The thing is that there are some photons which are continuously swapped between the source and the background model during the MCMC run, and this caused the identification of extra clusters, which are not really sources. Okay, so we need a kind of post-processing procedure in order to figure out which are the true cluster, the true sources, and which are just due to the noise effect of the background contamination. So, in particular, we want to discover the high posterior probability regions on the map. So, which are regions with a large probability that there is at least a source there, included there. We can do them just by looking at the posterior draws or the location parameter of the sources sampled by the MCMC algorithm. Because if there is an area in the map with lots of posterior draws, then it means that the evidence that there is something is very high, or is reasonably high. And also this procedure allows for a relabeling of the draws, because of all the draws inside a certain region can be relabeled according to that region. I just want to give you a fast sketch of the algorithm. So I just take the posterior draws of the location parameter for any iteration T1 to capital T, and for any mixture component. And obviously the mixture component number of mixture components changes for every single iteration. And we first divide the map into very small square pixel of a given size, which is very small, and this one is just given by the telescope. And then we look at all the pixels, and we select some pixels which are modal with respect to the number of draws falling inside. In particular, we select K star, that we can fix it. Maybe it can be 12, as we saw before, it was the model value. And so we look at K star model pixels. So these one are reference points, because we know that in those pixels, the evidence that there is at least a source is quite large. And we compute this probability by counting the number of iterations where there is at least a draw inside that pixel over the total number of iterations. If the probability is not enough large, we can extend this region by including the adjacent pixel in order to evaluate a region with a larger probability. And then we can relabel the draws. So I pass to the results because I think it's going to be clearer for you. This one is, for example, a pixel with a probability that there is at least a source which is estimated equal to 1, because for every iteration of the MCMC algorithm, there is at least a draw falling inside this pixel. And here, the green star represents the fact that effectively there is a source there. So this one is a true positive. And this is the same for region 2, 3, 4, but there are some cases, as I told you before, that you have to enlarge your area. For example, this case is including 2 pixels. So we are saying that by our model, the probability that there is at least a source inside these 2 pixels is equal to 1. And in fact, there is. And the grayscale represents the posterior distribution of the location of a source, given that there is just one source. So, for example, by looking at this case, we have 4 pixels. The probability that there is estimated that there is a source is equal, at least a source is equal to 1. And assuming that there is exactly one source, there is an high probability that it is in this pixel, a smaller probability that it falls here, and a very small probability for these 2 last pixels. And for the false positive, we have that the probability that there is at least an object inside is very, very small, as you can see here. So the model is working very well. So finally, to conclude, I just want to show you the results on a region surrounding, the data coming from a region surrounding the galaxy Antlia 2. Here on the left, you have the data with the pixel, and the brightness corresponds to a number of photons falling inside. And on the right, the reconstruction given by our p-spline Dirichlet process mixture model of the background contamination. So this is very nice. And at the same time, we identify some regions, actually 7 regions, with a probability larger than 0.75 that there is at least a source there. And effectively, they have sources inside previously discovered by the Fermi team of the NASA. And the probability, as I told you, is very high, as you can see. While there are two regions with sources inside, but not with a very large probability estimated by our model. And this is maybe due to the fact that some sources are quite faint. So a good thing to do in this case is to just use another kind of data like from lower energy bounds and re-estimate the model. And finally, we have 3 regions without any object actually discovered by the NASA, but with a reasonable posterior evidence. So the nature of these objects might be investigated in a more detailed, like they need a more detailed investigation. So to conclude, we provided a new Bayesian approach to perform the signal extraction of astronomical sources under the presence of an heavy background contamination. And our method is capable of reconstructing the background component by itself without any previous knowledge, locate the possible sources in the map, and finally quantify their intensities and their evidence. And future works will will focus on estimating the joint distribution of the spatial and the spectral information, so the energy as well, instead of using just the spatial information conditioned to the energy. So that's it. This is part of the team behind this project, this work, and thank you for your attention.
Thanks a lot, Andrea, also because you are very on time. So now you can close the presentation, and I call on stage Apostolos Chalkis. So thanks a lot to be with us today and to share your knowledge on the Volesti package. So if you can reach me on stage, please. Oh. Thank you. Good morning. Hi, nice to see you, to know you as well. Nice. And I leave you on stage to present, and please try to share slides and close your screen when you are ready.
Okay. So, can you see my slides?
Thank you. That's fine.
Okay, nice. Okay, so I start. Hi, everyone. I'm Apostolos Chalkis, and during this talk, I'm going to present open source package Volesti, which provides solutions to classical and difficult problems in computational geometry and statistics, and is based in high-dimensional sampling and volume computation. So package Volesti is an open source C++ package with an R interface or package in CRAN. It depends on some very famous C++ open source C++ packages as Eigen, LPsolve, and Boost. It currently provides 3 different algorithms for volume computation and 4 different algorithms for multivariate sampling. The main contributors of the package are Vissarion Fysikopoulos and myself, plus several community contributors. All the information about our package are included in our GitHub repository at the link you can see, or you can Google it. I think you will find it. So Volesti handles and offers solutions mainly for problems. So let's say that you are given a convex body P. The first problem is to compute the volume of P. The second problem is to sample from a distribution truncated in P, from any distribution, let's say, truncated in P. A third problem is to minimize the convex function in P. This is the general setting of convex optimization. And the fourth problem is to compute an integral of a function over P. So these are, as many of you I'm sure that you know, these are very fundamental problems that appear in many applications. So Volesti provides randomized approximation algorithms for these problems based on multivariate sampling from truncated distributions in P with geometric random walks. The geometric random walk is a special case of Markov chain. For example, here you can see a uniformly distributed sample or a sample from the exponential distribution, which is related also to convex optimization, the right plot. So considering first volume computation, there are 2 first thoughts that someone can have, very intuitive thoughts. The first one is to compute the triangulation of P and sum all the volumes of the triangles. The problem with this approach is that as the dimension grows, the number of triangles increases exponentially with the dimension. So for large dimensions, the number of operations that you have to perform explodes. The second approach, the second thought, is to sample from a bounding box and count the number of points in P. The problem with this approach is that the probability to find a point in P decreases exponentially with the dimension. So again, for high dimensions, the number of operations, the number of points we have to sample in the bounding box explodes again. So both approaches fail in high dimensions due to Kirchhoff dimensionality. The answer to this problem is an algorithmic technique that is called multi-phase Monte Carlo. There are several algorithms based on MMC. Again, I'm sure that many of you are familiar with this technique. The main idea is that you create you construct a sequence of simple Monte Carlo estimations, and then the number of operations you have to perform is efficient. So the only note here that the only alternative in R for volume computation is the package geometry, which performs exact computations. This is a very nice package and useful package for other geometric operations. But this is the main reason, the exact computation, it is the main reason that it fails to compute the volume for dimension, let's say, around 20. Here we give an example. We generate a random body, and we see that geometry fails to compute its volume, but Volesti needs just a few seconds to estimate it. Right? This is not the exact volume, but this is an estimation within our error 0.1, I think. Okay, so now considering convex bodies, Volesti supports 3 different representations of polytopes: H polytopes, V polytopes, and Z polytopes. A polytope is a generalization of the well-known polygon. A 2D polytope, we call a 2D polytope as a polygon, and the generalization of a polygon to arbitrary dimension is called polytope. So when a polytope is given by a set of half spaces, we call it H polytope. When it is given as by its vertices, we call it V polytope. And when it is centrally symmetric, we call it, and it has some other properties that we're not interested here, we call it Z polytope. Volesti also supports nonlinear convex bodies, as we call them spectrahedrons. And this is a very general case of convex bodies. For example, polytopes can be seen as spectrahedrons, or the ball or the ellipsoid can be seen as spectrahedrons. So Volesti is the first software that performs volume computations in thousands of dimensions. And at the table below, we demonstrate the 3 different algorithms that it provides. And we mark in which case each algorithm is faster than the others. Okay, so it also provides 4 random walks: ball walk, which is Metropolis Hastings for truncated sampling, 2 variations of hit and run, which is a very popular random walk, this random directions hit and run and coordinate directions hit and run, and billiard walk. The first 3 of them can be used to sample from any distribution in P, and Volesti currently supports 3 different types of distributions: uniform, Gaussian, and exponential distribution. And billiard walk can be used only for uniform sampling, but it turns to be very efficient and much faster than the other 3 for this distribution, of course. For example, here, which is a simple example of how we can use Volesti to compare mixing time, which is the speed of coordinates of a random walk, and we can use it to compare the mixing time for these random walks. So here we apply uniform sampling from the hypercube, and we project the points to R3. Each row corresponds to a specific random walk: ball walk, coordinate directions hit and run, random directions hit and run, and billiard walk. And each column corresponds to a different walk length. The walk length we call the number of consecutive points that we burn until we store a point. So usually we increase walk length in order to decrease the correlation between successive points. And the interesting about these plots is that the fourth row, where we can see that billiard walk behaves as almost a perfect uniform sampler, even the walk length is equal to 1. Another important operation, among others, that Volesti provides is rounding. So rounding is an operation that can be applied on a convex body, and we usually apply it on skinny convex bodies. The problem is that when we have a skinny body, and let's say that we want to sample uniformly distributed points from P, or from any distribution truncated in P, for example, here we have a skinny 2D cube. The problem is that almost all the random walks usually stuck in corners or in particular regions of a skinny convex body. For example, at the left plot, we sample directly from P, and we see that the samples of the random walk is concentrated in a small region. But at the right, we apply rounding on this skinny convex body. We sample on a rounded convex body. I don't give here any details, but with this operation, we are able to obtain a higher quality sample on a convex body. And the reason I show you this slide is that this operation, rounding, is useful to be applied on skinny convex bodies for if you want to sample from any distribution in P. So it's really a useful operation. And Volesti provides 3 rounding methods. Each one of them has advantages and disadvantages regarding the stability and the speed. Okay, so now the first application that I would like to discuss is multivariate integration. So let's say that you have a function f and you want to compute the integral over P. A simple approach, a very simple approach, like naive, almost naive approach, is to sample n uniformly distributed from P, and then take the average and multiply with the volume of P. So this is, of course, many of you would know that this is a naive approach, but the reason I show you this example is that even with this approach that Volesti can implement as the code shows below, we can estimate integrals using Volesti in higher dimensions than the existing R packages can provide. For example, here we compare Volesti against exact computation, in particular a combination of geometry and simplicial cubature. We use geometry to triangulate the body, to compute the triangulation of the polytope, and simplicial cubature to compute the integral in each triangle. And then we sum up all the values of the integrals. As you can see at the table below, Volesti is much faster when the dimension is equal to 15, and when the dimension is equal to 20, simplicial cubature fail to compute the integral, and Volesti needs just about 1 minute. Note here that Volesti is the only package in R that can estimate integrals over general convex bodies and not only triangles or simplices. Triangles in higher dimensions, we call them simplices. So, of course, this period we work on more sophisticated methods. For example, important sampling, which is a family of Monte Carlo integration methods that are very efficient, and there's a lot of work on this, of course, on this problem. The last application that I would like to discuss is an application in finance, in particular in crisis detection in stock markets. So here we use open data, public data, given by Stanford, and we take the returns of 52 popular assets. Volesti employs sampling and volume computation to approximate the joint distribution between portfolio return and volatility in a given time period. For example, we call this approximation as copula. For example, at the left plot, you can see a copula that corresponds to a normal period between March of 2007 and May, almost June of 2007. And that was a normal period in stock markets. And at the right, you can see a copula that corresponds to a crisis period between December of 2008 and March of 2009. This period is included in subprime crisis. Notice here that the mass of in each copula concentrates in a different diagonal. So that motivates us to define an indicator as the ratio between the two masses, the mass at the main diagonal over the mass in the other diagonal. If the indicator is larger than 1, we say that this copula is more probable to correspond to a crisis period. Otherwise, it's more probable to correspond to a normal period. So in this figure, what we done is that we computed all the copulas from 2007 until January of 2007 until October of 2009. And for each copula, we compute the value of the indicator and we plot this value. The red and the blue colors are not, they're nothing to do with the red and the blue color in the previous slide. So here we just mark some time periods as follows. When the indicator is larger than 1 for 60 consecutive copulas, we mark this period as a crisis period. And if the indicator is larger than 1 for more than 30 days, but less than 60, or not days, copulas, we mark this period as a warning period. Otherwise, we mark the period as a normal period. And here you can see that Volesti used public data and successfully detected the subprime crisis of 2008. Of course, there is a paper that you can find more details. So to close this talk, this year we are very happy to be a mentoring organization for Google Summer of Code. Volesti is the main software of Geom-scale organization. And we have 3 student projects this year. The first is sampling concave densities, convex optimization, and uniform sampling for machine learning. Of course, we have communication channels to communicate with other people. And all the information for our organization software, for example, how to contribute, documentation, and so on, a tutorial, of course. All this information can be found on our site or on our GitHub repository. So thank you. That was
Thank you, Apostolos, for this great presentation, also for sharing knowledge on Volesti, very impressive package. Thanks a lot for your work.
Thank you.
And just stay with us for the questions, and then I leave the stage to Riccardo. So Riccardo Corradin.
Can you hear me?
Good morning. Hi. So I leave you the stage, and please turn off the camera.
Can you hear me? Yes, that's fine. Okay, perfect.
Perfect. So when you are ready, you close your camera. Just try to share the screen. Thank you. I will stop you with when it's time.
Okay, now can you see the slide? I hope. Okay, so
yes.
Perfect, thank you. So I'm Riccardo Corradin. I'm currently a postdoc at Bicocca University in Milan, and as part of my PhD program, I've worked on estimation of Bayesian parametric mixture, and then going on coding about that, I decided to implement a package, and jointly with Antonio Canale from the University of Padua and Bernardo Nipoti from the University of Milano Bicocca. So I will introduce a bit the topic and Bayesian on parametric mixtures, and then I discuss a few details about the package implementation, and then I show you the highlights of the main features of the package. We are in a framework where we have a sequence of observation, assuming with a continuous support for the specific case of the package, and characterized by a sequence of latent parameters, and we assume that these parameters are exchangeable. And we can build up a mixture model using 2 main components, which are a kernel function defined on the support of the data times the support of the parameters, and a mixing measure, p tilde, which within this specific framework we assume to be an infinite probability measure, so a probability measure with an infinite number of components, and furthermore we assume that is random, distributed according to a random probability measure Q. So our mixture model is just the integration of the kernel with respect to this specific mixing measure. And due to the fact that is random, also the mixture model will be a random density. And these mixing measures are almost really discrete, so you can rewrite the model as summation of an infinite number of components. And the crucial part here are two things. First, estimate the random density, and second, estimate the allocation of the observation in different components of the mixture. So we want to make clustering and at the same time estimating this random density or the posterior distribution of this random density. We consider just mixing measure that could be represented as a steep breaking representation, just in the last equation, where you have mainly two parameters, a discount parameter penalizing some component and a strength parameter. And the last key quantity is a distribution P naught that is a diffuse distribution over the subtort of the parameter and is more or less centering the mixing measure. So it's like describing the probability allocation, mass allocation over the subport. And this model was first introduced for the Gaussian case with Dirichlet process mixing measure, then extended to the Pitt-Maillard process and with the introduction of the parameter sigma. And just to give you a sketch, a peculiarity of the Pitt-Maillard process is that the predictive distribution of the n+1 term given the first n term is a convex combination of the prior guess expressed in terms of P naught and the empirical measure over the already observed terms θ1, θn. It's known that this parameter sigma can be tuned and play a role on the reinforcement mechanism behind the model. And these models are useful because they have a good balance between flexibility of the model and tractability of the model. But we still have a problem that we have this infinite dimensional distribution P tilde. And most of the techniques to deal with this family of models relies to MC-MC approaches, mainly divided in two families. The marginal sampler that are sampling strategy that integrate out the distribution of the process P tilde, and the conditional sampler that work conditionally on a particular realization of the process. Sorry, I use process and mixing measure for the same things. And in the BNPmix package, we accommodate three different sampling strategies: a marginal sampler and a slice sampler that is augmented the problem with a latent variable U that is uniformly distributed. And once that you introduce this variable, the number of components that satisfy the condition in the indicator variable are finite. Is finite, so you just have a finite mixing measure. And we also propose an important sampling strategy to deal with the posterior distribution of this model, and this also in the package. Just a few details about the implementation. In the package, there are mainly two groups of functions: the main routines that are functions to estimate the model, and some activities to interact with this estimation and to help the user to interact with the package. And unfortunately, this strategy relies to MC-MC strategies that could be really slow and tedious, especially when the sample size grows. So we have implemented everything in C++ to keep down the computational time, mostly resorting to RCPP and RCPP armadillo libraries. And the main routines produce an S3 class object that called BNPdense with some particular feature that I will show you, and that the user can interact with this BNPdense object with some methods. And there are also other utilities that I will show you in a bit. And about the implementation of the algorithm, just a few words. The MC-MC strategies have a common structure. So at each step, you have to reallocate the observation in the components of the mixture. Then you have to update the parameter of the components of the mixture conditionally on the allocated observation. And then you have to update the summaries of the mixing measure. And eventually, if you want to relax your prior assumption on the model and setting also the hyperpriors, we have to update the hyperparameters. And this can be a bit slow, first, and second, you are updating a lot of quantities and is burning out your memory. So to push down the memory usage, everything is implemented in void function, and the user can eventually ask to push out the current state of the chain and save all the output, or if it is interested just in a subpart of the output, like the partition visited from the MCMC, you can it's possible to save just this particular argument. Okay, so the first function is the PY density function, and is estimating infinite mixture model with a Gaussian kernel, both in the univariate and multivariate case, with a Pitt-Maillard mixing distribution. And the function call is filled with a few arguments, y that are the data and can be either a vector or a matrix, and a list of arguments tuning the MCMC, like the number of iterations that you want to run the algorithm, the number of born-in iterations, the sampler that you want to use, or the model that can be location scale, or diagonal location scale, and explaining a bit, and other arguments. The prior list is a list of arguments specific for each model. So you pass the parameter specific for each model that you assume, and then an output list to tune the output that the function is giving you back. And all the function generated with this BNP dense class object. An example of the model, this is the Pitt-Maillard mixture model with location governed by the mixing measure. So you have that the data are distributed according to a Gaussian kernel with location μj group specific, while the capital sigma is common across all the groups. The mixing measure is acting only on the location μj, and you have a base measure that is the P note that I told you before, that is characterized by M0, S0, and then eventually you can assume hyper distribution characterized by the parameter M1, K1, lambda 1, and capital lambda 1. And this is a common structure across all the package. The parameter denoted with 0 are at the first level of hierarchies, and the parameter denoted with 1 are on the second level of hierarchies. This is consistent across all the function. And similarly, this is the same model, but including also the scale component, capital sigma j, inside the group specific component. So this, within this model, the process is acting on both the location and the scale. So μj and sigma j are group specific. But again, also here we have this common structure with the parameters where the 0 parameter act at the first level of hierarchies and the 1 parameter at the second level of hierarchies. Just an example, in the package there's this CPP dataset that is regarding a study within 12 hospitals about gestational times and pregnancies. And here, for example, we extract just the data for one hospital and the gestational time. We set up the prior, and all the details are in the manual. So centering the location in the mean of the data and the scale in the variance of the data. And we ask for the full output, and we run the model for 5,000 of iteration with 4,000 of Barney iteration, and we assume the location scale model with important conditional sampler. And by default, the plot method is extended to be integrated in the GG framework, so it's giving you back a GG plot. And you can tune a bit the plot, asking, for example, for the posterior mean of the random density, the credible band, or the partition with the scatter plot of the data. Again, all the details are in the manual. Similarly, we can consider the multivariate case, where at this point y is a dataset with 3 variables, and Similarly, we can estimate the model, and at this point, the plot is given back bivariate plot with the scatter plot of the data that you can ask by show class true false, and the posterior mean of the random density visited by the MCMC, and all the tuning parameter that again you can find in the manual. And similarly, we implemented the PY regression function that is again an infinite mixture model with Pitt-Mayor mixing measure, but the kernel at this point is a regression kernel. So Y is the response variable to feed the function, X are the quadrates, and the MCMC arguments is still a list, same as before, except for one parameter that is M-marginal, because at one point with this model you need a Monte Carlo integration, and this parameter is tuning the Monte Carlo integration. And model specific, you have a list of arguments to feed the function and to tune the base measure, the P-naught measure that I told you before, that is governing the probability mass across the support of the parameters. And you can tune also here the output. This is just a graphical representation of the model. It's similar as before, but instead mu location group specific. Here we have beta, that is a regression coefficient, and also the effect of the covariates on the response variable. Again, the parameter with no zero are at the first level of hierarchies, with one at the second level, and is consistent across the package and the manual, if you want to try it. And just an example, we set up X two-dimensional covariate and Y response variable. And then we call the function by assuming as prior the default value of the parameter. And you get back a model that is giving you an estimation of the mixed model with regression kernel. And if you plot it up to 4 covariates, it's giving you back a ggplot with the scatter plot of the group divided by this clustering structure, assuming a regression structure behind the data. And other important things, well, about the package, print and summary basic method give you back basic information. The plot, I've already told you almost something about the plot. You can export the BNP dense object to CODA to make some diagnostic on the output, and is integrated with the CODA framework. You can evaluate the density at a specific point, and an important method is that you can call this method partition on the object that is given you back from the function of the package, and starting from the partition reached by the CNC, this is the bell probably. Well, you can get a point estimation of the partition, and thanks for your attention. Please feel free to write me if you want to chat about Bayesian statistics, Bayesian nonparametric, and computational statistics. And thank you again.
Okay, thank you, Riccardo, as well for the presentation. So you can stay with us, don't leave, because we will have a round of questions. So please, also I ask to all the participants to join us. And please, Luís.
I can stop maybe the screen now. Okay, perfect.
Thank you. Apostolos, thanks.
Hi.
Hi, okay, so I can read for you some questions that we received from the public. Okay. So I prefer to share with you just one question each one, so you can make, I mean, a reply, not too long replies, please, but just a question for each, so you can go following the order of the presentation, please. So first question for Luís. So they are asking which statistical test do you use for spatial correlation, and if the code is available as well on GitHub page. Another question for Andrea Sottosanti. It is this one. Do you have any thoughts on why R seems not to be very popular in this field of astrophysics compared with to the amount of work done, for example, in Python on this field? The question for Apostolos is the following. Random walk and other stochastic processes can remain in local optima. Depending on your data, have you observed such occurrences? And have you considered using a hill climbing techniques to improve this feature?
Excuse me, I didn't hear the last question.
I can reply for you. So the question is if random walk and other stochastic processes can remain in local optima. So depending on your data, have you observed such occurrences? And have you considered using a hill climbing techniques to improve this feature? A question for Riccardo is this one. So can you add some more features on this package? Because at the end you were a bit
out of time, yes.
Yeah, so just two more features you would like to add, please.
Say it again, sorry. If I want to add some feature.
Yes, on the structure of the package, because at the end we have to see some details. So if you can just summarize very briefly other features of the proposal.
Okay.
And please reply in order of the presentation. So Luís, thank you.
Okay, thank you. Thank you for the questions. The first question is about the statistical test. I didn't use in this presentation when I show in the slide spatial correlation. It's just to show that you can visualize some clusters, and then you can come up. You can see that maybe you can find some spatial correlation. But you can use, for example, Moron's I, that it's one traditional test, and the Monte Carlo test to try to find to retrieve the spatial correlation. And yes, the code is available on the GitHub. The user, you'll have to look for the Voronoi, but not the I. It's Y. It's our user there. And in the next month, you will share the whole code and also one paper to explain better the methodology. And thank you.
So this is the time for Andrea to reply.
Yeah. So basically, I think that in astronomy, the astronomers usually use Python or prefer Python than R because of, I think, many methodologies that they use are not concerned with the concept of statistics and probability and this kind of things. So I think that basically when they develop their method, they really need a kind of programming language that is in a different level with respect to the programming, to the way of programming the things as the statistician can think about. So just part of the topics that physicists use and physicists treat are related to the statistics and probability, and that's maybe the reason why they don't use R so much, but they just prefer to still use Python because they use it also in other applications.
Thank you. This is the turn of Can you repeat?
Okay. The first part of the question, if random walks can stay on local optimals, the answer is it can stay, yes, of course, and this is a problem. And I think this is a criterion how good is the mixing time of a random walk. In our experience, what we do is that the most part of the existing work in theoretical work is about uniform distribution and local cave sampling, speaking about truncated distributions. So when you have a low concave distribution, you have just one global maximum, or if you look at the convex function, you have just a minimum. And to staying on the local optimum, actually, this is something that we want to exploit in order to solve a convex optimization problems. Because if you sample with small variances from a low concave distribution, you know that you are going to be close to the optimum with high probability. But if you don't have such good densities and you have more anomalies and more optimums and so on, the best answer that we can find until now is samplers like Hamiltonian Monte Carlo, which it's very efficient and the mixing time is actually very good, and it's almost we need almost constant number of steps in order to converge to the target distribution. So about hill climbing techniques, the answer is no, that we don't we haven't used these techniques, but I think it's a very interesting idea. Yes, of course.
Thank you very much for your reply. And this is Corradini time. And another question for Riccardo is, how do you choose your kernel?
I saw it on Slack, okay. So about the first question, other features, well, the package is accommodating also other type of model. There is a subfield in Bayesian nonparametric that is modeled for partially exchangeable data. So you have the data divided into subgroups, and you assume exchangeability just within groups, but not across groups. And you want to borrow information across different groups. And the package is accommodating also this family of models for a specific kind of model in this large family of models. And about how you choose the kernel, well, the kernel here is just, we consider just a continuous kernel, and the choice is the Gaussian kernel for a particular reason. There is a paper of 84 about law, and an infinite mixture of Gaussian distribution is dense in a space of regular densities. So there is this theoretical guarantee that, in fact, you are modeling a random density that they support in the entire space of regular density if you use an infinite number of components. This was the main reason to the choice of the kernel for a Gaussian one. But I'm working on extending to other kernels. As for the GLMMR, I miss the acronyms. I don't know what are GLMMR. I don't know if someone of you know the MR finally what is, but I don't know. Okay, no?
If you don't mind, we have closed the section, so please.
Okay.
Okay.
That's all.
Okay, thank you, because we are just on time now to close the section. So I think that there are other questions you can see there. So you can also keep in touch directly with the speakers that I really thanks for your time, your presentation, and thanks for sharing also the code, if you like, on this chat. And I just have to remind you that during the lunch there will be a thematic lounge, so you can attend it. You are invited to be present as well during this lunch time, and it will be on. To share ideas as well, and there will be also occasion to meet some sponsor. So please join all if you have time, and if you would like to share, to know someone also in this virtual environment, but it is very useful as well on this time. So thanks a lot, and I hope to meet you again in another conference, maybe in person, and have a good time, and also go on with the work, which is very interesting, really. So thank you, and see you in the afternoon.
Thank you.
Thank you.
Bye.
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 Bye.